Hi, Alex Plager here, and today we're going to look at Felix Baumgartner's world record free fall. Felix Baumgartner broke the world record for the highest free fall, the highest manned balloon flight, and the fastest free fall, all within minutes on the same day in 2012. He jumped from 36,402 meters up, which is 127,000 feet, or equivalently known as almost 24 miles. And the one record he didn't break, he purposely left intact for his mentor during his time training out of respect for the guy. So, our purpose for this lab is going to be modeling Felix's 4-minute and 20-second free fall. We're going to be mainly using principles from Newton's second law. However, this time we're going to be accounting for drag, and it's going to play a huge part in our model. So, questions we're going to want to think about over the duration of this lab. We want to know how the change in temperature with altitude will affect our model, and if Felix's temperature increased as he fell, and if it did, by how much. And what's the minimum height Felix could have opened his parachute at and safely survived the fall. So in this problem, we're going to be using Newton's second law, and we're going to be modeling the two forces acting on Felix as he falls, which we're going to be taking into account, which are the force of gravity and the force of air drag on Felix. Gravity is going to be modeled using bodies from distant from the surface of the Earth, as Felix's 24-mile altitude is significant enough to warrant not using the MGH equation that we're familiar with. And force of drag is going to be this complicated equation, being -1/2 times the air drag constant times Felix's surface area times sigma as a function of altitude times velocity squared. So to initialize the variables in this equation, little m is going to be Felix's mass, which is 117 kilograms. Big M is going to be the mass of the Earth, which is known as well. Z is going to be a function of Felix's altitude as he falls from his 24-mile ascent. CD and A are going to be the constant for air drag and Felix's surface area, perpendicular to the direction of motion. We're going to assume that C, D, and A are going to be relatively constant, so it'll make it more easy to calculate, assuming that Felix remains stationary as he falls. And sigma is going to be a function for air density as a function of height in the atmosphere, as different layers of air in the atmosphere have different densities. So in order to solve this, we're going to be solving for air pressure as a function of height, which will factor into air density as it's a variable in that equation. And we'll use those equations to calculate the air density at a given height. So how are we going to be making our model? We're going to be splitting Felix's fall into 3 groups of time. The first stage of his fall is going to be the subsonic fall, which is defined as him traveling, his airspeed being anything less than Mach 0.8. And this coincides with the first 45 seconds of his fall. And for this stage, in our model, we'll assume that drag is very low because the atmosphere is extremely thin. And what that means is our CDA value is going to be 0.18. The second stage of his free fall is going to be his transonic to supersonic speeds. Transonic is defined as anything greater than Mach 0.8 but less than Mach 1. And this coincides with the 45 seconds up until the 75th second of his fall. So, as Felix's velocity approaches Mach 1, air drag is going to increase dramatically as he approaches the sound barrier, and as a result, CDA is going to grow almost by a factor of 4 to 0.73. And the third stage of his fall will be the second subsonic speed. So this will be from 75 seconds onward to where he deploys his parachute at the 260th second of his fall. And air density has become increasing rapidly as Felix is entering the troposphere, and his altitude is considerably lower, so his CDA value is going to be 0.85. So now that we've executed our model and completed it, we can answer the questions we set for ourselves at the beginning of the video. So our first question was, does Felix's temperature increase as he falls? Yes, of course it does. The force of drag is exerting a force on Felix, and this is known as friction, which also increases internal temperature. However, unfortunately, it's difficult to determine precisely how much his temperature increases, as we don't know the specifics behind the thermodynamic properties of the suit Felix is wearing during the jump. Our second question is, how does the change in the temperature of air affect our model as the altitude varies? Well, Felix passes through 3 layers of the atmosphere: the upper stratosphere, the lower stratosphere, and the troposphere. And within each of these layers of atmosphere, the density of air is different, and the temperature of air is different as a result, because the upper troposphere contains the ozone layer, which is much better at retaining temperature, for example. So, conveniently, NASA has a couple of functions to describe the temperature in each specific layer of the atmosphere as a function of height. Or, in the case of lower stratosphere, it's actually a constant value. So you can see that in these three equations here, which is how temperature is calculated. And the reason temperature is important in our force of drag equation is because temperature affects the air pressure at a given height z, which in turn also affects the density of the air, which happens to be a direct variable in our equation for the force of drag. And finally, we wanted to know what was the minimum height Felix could have safely opened his parachute, and that would have been 1,600 meters. It would have taken him about an additional 10 seconds to fall this distance. However, it would have been right on the edge, and since the jump was so dangerous already, it was a needless risk, and so Felix deployed his chute early at 2,600 meters.